Alright guys, this is Mr. Brengle and I will be going over the worksheet Little Dudes number 1. If you've not already read the directions, go ahead and pause the video and do that now. So the first thing we're going to do here is we're going to look at this what we'll refer to as a motion map with the little dude here. And when the clock reads 0 seconds, he's at 0 meters. Okay, and then we're just going to go down the line here. We're now at 2 seconds and he's at 4 meters. And then 4 seconds and 8 meters. 6 seconds and 12 meters. And then finally 8 seconds and 16 meters. Okay. Alright, so let's move along here. It says write the equation for finding speed given a distance. Okay, the difference between two positions and the corresponding interval, the difference between the two clock readings. After writing the equation, apply it to find the speed of walking dude. Okay, so the equation for speed here, V is equal to change in position over change in time. Okay, so what we want to do is we want to look for the final position. So you could also write this like this. You could put this in parentheses and say his final position minus the little dude's initial position over the final time minus the initial time. Okay, so if we look right here, we need this now. Let's go ahead and do this math here, and I'll change the color here into blue. And so I'm going to do it. I'm going to do it like this over here. So, okay, the final position that he had was 16. So 16 meters minus the initial, which was 0 meters, over 8 seconds minus 0 seconds. Okay, so obviously that one's pretty easy because it started at 0, but it's going to be 16 meters over 8 seconds, which is then going to reduce to 2 meters per second. Okay. So the next thing we need to do here is plot the points from the data table right here on this graph. So for this, go back to the red pen here. I'm going to mark at 0, 0. That was our starting spot. And then I need to look at 2 seconds and up at 4 meters. So right here. And then we're going to 4 seconds and 8 meters. And then 6 seconds and 12 meters. And then 8 and 16. Okay. And then we would just connect those dots there. Okay. Alright, so what assumptions about walking dude would we have to make if we wanted to connect the dots on the graph to form a straight continuous line, which I have already done? Well, the assumption that we need to make there is that walking dude is moving at a constant velocity. Okay. All right. Go ahead and move that right there. Okay, so we're now on to page 2 of Little Dudes 1. So you can see number 5 there pertains to the last page. It says make those assumptions, draw the line on the graph, which we already did. So we'll move on to number 6 here. What does the notation delta t mean, and what is delta t between 5 seconds and 8 seconds? So the notation delta t stands for change in time. And really, any time that you see that delta right there, Greek symbol, that means change in. And then whatever variable comes after that is what it's referring to. And in this case, it does say delta t between 5 and 8. So for this, we would say that delta t, if I can get this to work, is equal to 3 seconds. Okay. So then right here below it, it says, what does the notation delta x mean? And what is delta x between 5 and 8? So again, it's change in this case, position. So we need to know what the change in position is between 5 seconds and 8 seconds. So let's actually go back to the last page here, and let's go look at that between 5 seconds and 8 seconds. So really what we're looking for here is in this, from here, 5 seconds to 8 seconds. Okay. So what we want to do is we want to kind of trace this over here. And you see that it's at 10 meters to start with, and then its final position is over here at 16. So 10 and 16. We'll go back to this page. And so you may, when you're actually doing this here, you may want to write it as final minus initial. So if we did x final minus x initial, this would be equal to 16 meters minus 10 meters, which is equal to 6 meters. Okay, so number 8, what relation can you use to find the slope of the graph in terms of rise and run? So I know this is kind of a confusing question, but all it's really asking you to do is, sorry, I'm technical difficulties here, is say that slope is equal to rise over run. Okay, so then number 9, what quantity represents rise on our graph? What represents run? So if we actually go back and we look at the last page real quick, the rise is talking about our y-axis. So in this case, that would be the position. And then the run would be the time. So we'll go back over here. And the rise is our position, which I'm just going to say POS, and then the run is time. Okay, so what equation would you use to determine the slope of a position versus clock reading graph? Do not use any numbers yet, simply state the equation. Does this equation look familiar? If not, it is wrong. Okay, so the equation determines slope here, for us, if we were doing rise over run, if that's what slope is, then we would want to say that, I'll actually put, so rise over run. Okay, and our rise would be delta x, right? Our change in position. And then the run would be the change in time. And so it's asking you, does this look familiar? And you are hopefully saying, yes, that looks super familiar, because Mr. Brengle already showed us in class that speed is equal to change in position over change in time. Okay, so we'll move on from there. And it says, apply the equation to determine the slope of a walking dude. So what we need to do here is, actually we have already done this in a previous question. If we go back to this page here, we actually already did this right over here. We looked at little dude's change in position over time, and we determined that the speed was 2 meters per second. And so that would be the next thing here, is just that you guys recognize that the slope of a position versus time graph is going to be your speed or velocity. Okay, so we'll go ahead and move on here. Number 12. It now wants us on the front page, so we're going to have to flip back and forth here. Plot position versus clock reading for the other two little dudes shown below. So I'll need to use some different colors here. So we will kind of have to flip back and forth, which may be difficult, but let's go with blue here. So we've got 0, 0, and 2, 7. So I'm going to kind of get rid of some of this extra stuff here. Bear with me. So we've got 0, 0. And I already forgot what the last one was. 2, 7, and 4, 16. So 2, 7, 4, 16. And then 6, 24, which is going to be the last one that we're really going to put on there because it's going to be way up here. So we can connect these like this. And then we can look at the reading dude over here on the right side, which I'll change this to yellow. So you can see that his position, no matter the time, is actually always at 8 meters. So we come back over here, you can plot these points straight across. Okay. So then it says, what would align with a shallower slope than that of walking dude mean? So let's go back over here and so we can look at these two lines here. We had our original walking dude, which is the red and the black, which I'll go ahead and change that. We'll just make that red. So red is our original walking dude, and blue was walking dude 2. And so the shallower slope there means that the speed is lower, right? So the steeper the slope, the higher the speed. So we'll come over here. Okay. So what would a line with a negative slope mean? Well, this is where it becomes important to distinguish between speed and velocity. So a line with a negative slope would just mean that you were traveling in the opposite direction. Okay, so if you have a positive slope, you're traveling in the positive direction. A negative slope, traveling in the negative direction. So I'm just going to write negative direction. Okay, what would a vertical line on the position versus clock graph mean? Well, before we answer that, let's just look at this for a second. And if there was a vertical graph on there, or I'm sorry, a vertical line on there, you would essentially be saying, in fact, let's put one on there. So we're just going to put one out here at 9 seconds. I'm going to put this vertical line. Well, that means that in the course of no seconds, you have traveled 18 meters, which, my friends, means that you have discovered time travel. So that's excellent. Okay, last thing here, number 16, draw a line parallel to the position versus clock reading graph of walking dude, but start at 0 seconds and 8 meters. It's the graph for walking dude 2. What's different about walking dude 2? Okay, so we need to draw a parallel line starting at 0, 8. So we need to go back here. Parallel line at 0, 8. So I'm going to do this one in red as well, just so we're all... Oh, I think I kind of messed that up there. It needs to go like that. Okay. Alrighty. what is different about Walking Dude 2? Okay, so the important thing to know here, which I'm going to label this one number 1 and this one number 2, is that there's really nothing different about these two Walking Dudes. They're traveling at the same speed because they have the same slope if they're parallel lines. The only difference is that Walking Dude 2 is starting 8 meters in front of Walking Dude 1. So that would end up being your y-intercept in our physics equations when we talk about that. So you always need to take note of that. All right, congratulations, you have finished Little Dudes number 1.